There has always been two clear ways in which we might discover alien life. The first is, of course, SETI, or the search for extraterrestrial intelligence. The second is the search for non-intelligent or simple life. The first is done at a distance. The second can be done here in our own solar system. Up until now, it's always been assumed that the two would only be generally related. You might see radio emissions indicative of a civilization, or you might see something like the vegetative red edge, indicating a general biosphere of photosynthesizing plant analogs. But there may be a way for technology to combine with biology and allow for intelligent life to communicate through life itself, and even pass on vast amounts of information through this method. My guest today has recently released a paper and also devoted a part of his latest book, The Case for Space, links in the description below, on this very subject, opening up an entirely new way to search for alien life.
Welcome to Event Horizon with John Michael Godlier. In today's episode, John is joined by the founder of the Mars Society, Dr. Robert Zubrin. Dr. Zubrin is an aerospace engineer and inventor, and he's the author of The Case for Mars, Merchants of Despair, and science fiction novel First Landing. Dr. Zubrin has also recently authored The Case for Space, How the Revolution in Spaceflight Opens Up a Future of Limitless Possibility, which is available from Amazon.
Welcome everyone to Event Horizon with me, John Michael Godlier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Robert Zubrin, welcome back to the program.
Thanks for inviting me.
Now, Doctor, you have a recent paper out, published on Paul Gilster's blog, Centauri Dreams, which is something a place I recommend for anybody that listens to this show. You should read that blog. Now, Doctor, you present a new way of detecting alien life, essentially, a new way of practicing SETI, or at least the search for microbial life in the universe. Can you give us an overview of that?
Sure. The paper is entitled Interstellar Communication Using Microbes. In the beginning of the paper, I discussed the problems with the current search, which is looking for radio transmissions from extraterrestrials, which has not turned up anything. And I think there's a couple of reasons why it hasn't. One is that it's actually not a particularly efficient way of communicating across interstellar space. You would need tremendously powerful transmitters and keep them on forever to have a chance of communicating with everyone or anyone. And furthermore, you'd have to know that they were listening. I mean, until the 20th century, anyone could have blasted radio at this planet for the past 500 million years, and no one would have been able to pick up a radio signal because nobody had a radio to listen with. For 500 million years, the Earth's atmosphere had plenty of oxygen. They would have known there was life here, and they might have tried to transmit, but dinosaurs weren't listening. The trilobites weren't listening. The ancient Egyptians weren't listening, And if they did broadcast to us now, who knows if we could even recognize it. So there's that. And then there's another problem with it, which is that it's not adaptive. Where's the upside to giving away your position in interstellar space? I mean, what if there are other species that might view you as a threat and do something about you? So that doesn't really have any motive. Now, there's another way to communicate, though, and that is, of course, instead of sending radio, one could send letters, one could send solid objects, one could send someone a book. And if you were going around the neighborhood and trying to tell stories to children, the radio transmission method is like going around in a car, blasting a bullhorn at houses and reading stories to houses, not even knowing if there are any children there, or if they speak your language, or anything of the sort. And and you get out of breath on doing that too. On the other hand, you could leave copies of a children's book on the front porch of every house, and you'd have a chance of reaching someone, and it'd be a lot less effort. Of course, if you try to send millions of books out into all the stars, that could get expensive, but there's a way to do it in which the books replicate themselves, and that is microbes. Microbes have DNA, and the average bacteria has about as much information in its genome as a 300-page book. And furthermore, it can duplicate itself. It can print more books so that you can both print a lot of books yourself, and furthermore, it can print the books when it gets to the other planet. So one microbe lands on a planet. Well, who's going to find that microbe? No one's going to find that microbe, but when it reproduces itself 1 billion times, someone might find it. Now, however, I don't think the kind of message that would be sent this way is what you ordinarily hear about from SETI people, the Sagan paradigm, where first you send a secret number like pi, which is something that any mathematician would recognize. And that basically says, hi, I'm an intelligent life form. Here's the value of pi. And now that you're listening, here's our dictionary so you can speak our language. And now that you can speak our language, here's the plan for building starships. Okay, this is sort of like what's in the movie Contact. I don't think that makes any sense. I think if you're sending information through DNA, the message is the genes. And what is the message? What's the kind of message that we send to people that we don't know? It's be like us. Propaganda. Think Radio Free Europe, think Radio Moscow, be like us. Or to stick with the book analogy, think of the Gideons, leaving Bibles in hotel rooms in the hope of converting people to become religious Christians. Be like us, okay? And they don't have to hang around the hotel room forever and ever. They just hope you pick up the book. What's the biological equivalent to that? Sending genetic information, which is not meant to be read by a cryptanalysis using a code-breaking code, but which is meant to get into the biome of organisms there, to mutate them, to guide their evolution. The mutation is the message. Now, bacteria can insert genes into organisms, and organisms can have genes that they're not using right now, but use later. Or they can have genes that they used to use, but don't use anymore, but could use later. Like a number of years ago, some scientists took some chick embryos and they activated some inactive genes in them. And guess what? The chicks were born with dinosaur traits. They had teeth. Okay?
Chickens with teeth.
That's right. Now, birds, we know, are in fact descended from dinosaurs. The earliest birds did have teeth. They were dinosaurs. The dinosaurs, the scales turned into feathers, the teeth went away and turned into beaks. But the long ago ancestors of birds did have teeth. And guess what? They still have the files on hand. So if time should change and birds need teeth once again, they won't have to evolve them a little bit at a time. Birds will be born with fully developed teeth. Just like, before I now run a small aerospace company. I'm a businessman. Before that, I was an engineer working for a large corporation. If my business should fail, I could go back to being an aerospace engineer for a big company. Before that, I was a high school teacher. If I can't get a job that way, I could go back to being a teacher. Before that, I was a cab driver. I still have the files, as it were, of my previous careers. And if I was forced back into one of those previous incarnations, I could do it. So life forms have that. Well, you say, okay, that's not too surprising. Birds once had teeth, so they could have it again. But what if we were to find in the genomes of organisms not plans for past traits, but plans for future traits? Okay, this would be very interesting. Once again, any mammal, humans, mice, all have fish genes in them, and they actually manifest themselves in the early development of the embryo. The embryos of humans and mice and dogs and cats all have gills, just like fish. Okay, then they go away as the embryo develops. It recapitulates the evolution of the species. Well, okay, once again, that's not surprising. We are descended from fish, so we have some fish genes in us. Okay, and the capability of manifesting fish traits. What if we found mammal genes in fish?
I see.
What if there were forward-looking traits? That would mean that somebody was sending genetic information into our biosphere, say, offering suggestions for future evolution.
How would geneticists look for that?
Well, you could try to activate such genes, just like the biologists did with those chicks, and see if you could activate some mammal genes in fish. Maybe you could create fish with lungs. Actually, there are some fish with lungs, but maybe you could create a kind of fish that has lungs that is not a lungfish, something like that. That would be one way to do it. The other way, look, basically you can either look for the messages or you can look for the messengers. Now, the messengers are bacteria being sent across space. Now, actually, it's pretty easy to send bacteria across space. They're so small that the light pressure of a sun on them can shoot them up to very high velocities. If we shot bacteria into space from the Earth and just had them outside of the Earth's gravity, but about the Earth's distance from the sun and just orbiting in space, the pressure of sunlight would shoot them right out of the solar system. It would send them to other solar systems. So you wouldn't need rocket ships for them. They basically have sails capable of catching sunlight and accelerating to interstellar velocities. And this has been known in the past. It's known as Panspermia. Now it's been objective. Well, ultraviolet light would kill them. Well, it would if they were naked, but half a micron of carbon of soot would protect them from that. So you could very easily engineer micro sailcraft designed to carry bacteria and mass produce them and release them into space. They would look like dust particles that would carry them, boom, all over into interstellar space. So there could be micro sailcraft arriving in the Earth's stratosphere. And by the way, because they're so light, if they were to hit the atmosphere of a planet, they could slow down without heating up. They have what we call a very low ballistic coefficient. We could look for these things floating around the Earth's atmosphere. Now, one problem there is there's so much life on Earth. You say, how do we know that these bacteria you find in the stratosphere didn't come from the surface? Now, okay, let's look for them in the atmosphere of Mars. Let's look for them in the atmosphere of Venus. Let's look for them in the atmosphere of Titan. These are all places where they could arrive and get caught and be floating around. So we could go looking for the messengers, or we could look for the messages, which would be found, or if they exist, they'd be genome scientists could find them either by sequencing the genomes and looking from that way, or by activating what appear to be dormant genes, junk DNA. In other words, those genes in those chicks that those biologists activated, those were not active. They weren't doing anything. This is just junk DNA. It's like walking into a building and there's a bunch of switches turned off and you start turning on switches and you see if some fans start coming on or some lights start coming on or what happens, or if a sound system comes on and starts blasting music at you. In other words, there's a sound system in this building and it's got symphonies recorded in it and they're ready to come out as soon as someone throws the switch. Well, that's what they found when they activated those genes in those chicks. So who knows what's in there?
It's worth noting, too, that nature, in the microbial world, nature can produce astonishing things, especially in regards to space. There are several species of bacteria that we know about so far that can absorb enormous amounts of radiation, the radiation of space, and they can dry out completely and do things that, well, for example, a Thermococcus gamma-tolerans can absorb like 25,000 grays of radiation and still be viable, whereas a human can absorb about 5 and it kills us.
Right.
So we have examples in Earth's natural environment of organisms that could survive in space. And imagine what you could do if you... Right. Yeah, imagine what you could do if you could engineer it.
Well, yes. Well, the very fact that they have such adaptations that allow them to survive space radiation is one reason to suspect, anyway, that they did come from space. Okay? If you see someone walking around on the beach wearing a life preserver, maybe he came from a ship. That's basically what you're looking at. Now, another point about this idea is as follows. While sending radio transmissions across interstellar space has no adaptive value, sending bacteria carrying the genes of your species, or at least of your general type of animal, across space does. It's reproduction. Propaganda is propagation. And, you could ask, well, why would they want to do that? Well, it's simple. Those that do it are the ones that we would see. It's why all of my ancestors were parents. Okay? So, well, why were they parents? Well, if they weren't, they wouldn't be my ancestors. It's that simple. And so if there's life spreading throughout the universe, there's a good chance it's being spread by those who like to spread their kind. Okay? And there it is. And, look, here's a fact, that life appeared on Earth almost immediately as soon as it could. Almost immediately. We have fossil residues from life on Earth going back 3.5 billion years that are incontestable, and some that people debate going back 3.8 billion years. And that takes us right to the period when the Earth was just getting cool enough to have liquid water, that it wasn't being bombarded so much by incoming meteors that it could be cool enough and actually have liquid water. So virtually as soon as the Earth could support life, it did. Now that means one of two things. Either the emergence of life from chemistry is something that's so easy that it just happens as soon as it can, or it means there's life floating around in the universe, and as soon as a planet becomes habitable, it seeds it. It's one of the two. Either way, it means life is common in the universe. Either it originates swiftly wherever it can, which means it's common, or it lands as soon as it can, which means it's common. So life's everywhere. But why a particular type of life? Well, the kind that you would see would be the kind that wants to reproduce. And this would be the way to do it.
So in other words, you could start sending out genomes into the universe and seeding life, right?
Right. You could seed life itself to make sure that the planets have life, but then you could try to influence the evolution to your kind of life. In other words, it's basically you're throwing in suggestions into other biospheres. Hey, try chlorophyll. Try respiration. Try backbones. Try lungs. Try warm-bloodedness. Try large brains. How about it? In other words, you could be throwing these suggestions into biospheres to try to reproduce your kind of life. And once again, why would someone want to do this? No reason except that the ones that do are the ones we would see.
And on that, we have to take a break.
If you'd like to support Event Horizon, you'll be pleased to know we've recently launched a Patreon. Link in the description below. Or alternatively, you can use your cellular telephone to scan the assemblage of squares on screen now.
Hi, I'm Dr. Robert Zubrin. I'm president of the Mars Society, and I'd like to invite everyone to come to the next Mars Society convention. It's going to be at University of Southern California, which is in Los Angeles, October 17th through 20th. We're going to have sessions there discussing the current Mars exploration program, the plans for human exploration, NASA's program, SpaceX's program. We're going to have debates. Is the lunar orbit gateway something necessary, or is it a diversion? Should we have a planetary protection program, or is this an obstacle to Mars exploration and settlement? What about the terraforming of Mars? Is it possible? Is it ethical? Can we do it? What does it mean if we do? We're covering the gamut. There's an open call for papers right now at marssociety.org. If you want to speak there, send in a 300-word abstract. We're going to have a contest. Mars Society is running a contest for people to design a 1,000-person Mars colony, including its technical aspects, its economics, its social, political, and aesthetic aspects. We've had over 100 entries. The 10 finalists will be presenting at the conference in front of a panel of judges, and the winner will win a $10,000 prize. That'll be interesting too. And there'll be a lot of fun stuff as well. I hope you can make it.
And now, back to John.
And we're back with Dr. Robert Zubrin. Be sure to like, subscribe, and hit the bell for this channel if you want more content like this. Now, this opens a can of worms, because if life arose on Earth very rapidly, as it appears to have done, as soon as it could, even maybe if we find that the chemistry of life is hard to get going, there are scientists looking into that, successors of the Miller-Urey experiments and all of that. If we find that the chemistry of life is extremely difficult, then shouldn't we strongly suspect that maybe this process occurred and that maybe we were seeded by a civilization somewhere out there?
Yes, it's quite possible. There's another mystery of life on Earth, which is that we find no evidence of any life on Earth, any free-living life on Earth, simpler than bacteria. And bacteria are by no means simple. They are extremely complicated organisms. They have all these organelles. They have a fully developed method of communication from one generation to the next using DNA and RNA. In other words, it's a fully developed language and alphabet. We use the Latin alphabet. There's some other cultures that use different alphabets, but we don't expect that cavemen had alphabets, let alone as their primate ancestors. This had to be developed over time. Okay, language is something that developed over time, and written language developed over time, and bacteria have it all. So the fact that bacteria appear on Earth without any evidence of more primitive ancestors does suggest that they came from space. Now, if they came from space, did they come through a natural process or did they come through intentional process? That's something it's going to take some work to sort out. The fact that panspermia through natural means is possible, and I do think it is possible, across interstellar space, and I've written papers explaining that. And by the way, there's some discussion of all this in the book, The Case for Space. That does make the problem more complicated. We're going to have to be able to sort out a natural insemination from an artificial one. But I think with enough work, we can.
Now, if you're talking in terms of the solar system itself, interstellar panspermia aside, we also have this idea of interplanetary panspermia, where life may have arose on Mars first and was delivered here, or for all we know, Europa. How do we determine if life on Earth actually originated here or was planted here microbially just after Earth got nice enough for it to support life?
All right, well, here's the thing. If you go to Mars, and if you find no evidence that Mars has life or ever had it, that would mean that life originated on Earth by itself, because if there were seeded from the outside, Mars would have been seeded too, okay? If you go to Mars and you find that it has or had life, but of a completely different type than Earth life, that it doesn't use DNA and RNA, it uses a different alphabet, that would mean also that life originates naturally where it can, because if they're different from each other, it means they weren't seeded from a common interstellar source. Okay. But if you go to Mars and you do find evidence of life and it uses the exact same method of DNA, RNA method of communication, okay, well, that could mean that one planet seeded the other, or that they were both seeded from the outside. Now, Earth life looks like it was seeded because it has no ancestors to bacteria on it. Well, okay, did it come from Mars? If we go to Mars and find DNA, chemistry, bacteria, as well as more primitive representatives, then that would show that Earth life did come from Mars, that Mars originated life and then it seeded the Earth. But if we find nothing, if we find that Mars was seeded too, that would suggest they were both seeded from the outside.
Was Mars nicer earlier than Earth? In other words, was it a better place for life to arise than Earth was when we start seeing evidence of Earth supporting life just after the late heavy bombardment? Was Mars nicer just slightly earlier, or do we even know?
I think it probably was a bit nicer a bit earlier because it's smaller. It would have cooled faster. But the early Mars and the early Earth were quite similar.
And possibly even the early Venus, too, which, I mean, that's an open question as well. Was Venus once a water world, essentially?
Right.
And which water world was the most clement for life very early in the solar system? I hope we can answer that question, because it's interesting, this idea that we may not be native to this world, which makes a case that we need to go reconquer the original home world, humans back to Mars, or Earth life back to Mars if it's not present there already. But so to condense this, we would be able to tell where life arose. Ultimately, just by looking at, we see precursors to bacteria on Mars. We don't see this on Earth. We see precursors. That means we must be from that body. Can we do that on an interstellar basis? Can we figure out if interstellar panspermia occurred?
Well, that's what I mean. If we don't find, Earth could have been seeded from Mars. And if so, we'll find pre-bacteria on Mars. But if Earth and Mars both look like they were seeded from the outside, well, then I think we're looking at an interstellar source.
Now, my last question is, all right, we have a sort of, you mentioned early on that it's really inefficient to build a giant omnidirectional radio beacon blasting out terawatts of energy.
Well, no, it couldn't build omnidirectional. It would have to be very directional.
It'd have to be, yeah.
And even so, it would require huge amounts of power.
As I recall, though, the original paper on that was Morrison and Cacconi, and they actually thought omnidirectional, right? Or do you remember that, where they were saying, well, we should look for these to see if they're even there? But I think it was because that's all we could look for in the 1960s, realistically. Now we can look for stuff much more targeted.
They were pointing radio telescopes at SETI, so they were not using an omnidirectional receiver. They were using a very directional receiver.
So, in other words, the most efficient way to do this would be bacteria. What's your thoughts on like von Neumann machines to do this technologically? Does it make more sense to send a bacteria or to 3D print out a bacteria using technology?
Well, bacteria are von Neumann machines. That is, if back, I don't know when, 70s or 80s, a visionary named Eric Drexler wrote a book called Engines of Creation, in which he talked about nanotechnology, building machines out of molecules. And these machines would be able to reproduce themselves. So you'd make nanorobots. But that's exactly what bacteria are. They are self-reproducing nanomachines. So the question is, can you program them to do what you want them to do? Well, to some extent we can. We can program them to make various chemicals for what have you. Can you program them to do more complicated things? Certain ways you can program them to insert useful genes in other organisms. If one was to get more sophisticated about this, you might be able to program a whole program of bacteria being sent in waves to other planets to initiate and then guide the evolution of a biosphere. I mean, the example I give in the paper is consider a parent trying to guide the intellectual development of her child. So she leaves books around the house. Okay, well, she leaves some letter blocks. She leaves some picture books. She leaves some chapter books. And she leaves works of great literature. Well, the little baby, it doesn't relate to the books, but it relates to the letter blocks. When it gets a little older, now it's 4 years old, well, those picture books start to become interesting. And then when it's 8, it can start to read, the chapter books, and then Harry Potter, and then War and Peace. So you don't even have to send these genes into the biosphere and time them. You can send them all into the biosphere, and as soon as the biosphere becomes mature enough to make use of them, it does.
So when we think about these things, when we think about SETI, we're thinking about radio telescopes and, how hard that actually it would be to pick up an alien signal. You're looking for a needle in a haystack, essentially, as you point your telescope directly towards a star system to see if there's anything there, and it gets very cumbersome. And then we're talking about things like using the James Webb telescope, if we ever get the thing in space, to look at exoplanet atmospheres and things like that, try to characterize atmospheres and look for red edges and things like this that might indicate biospheres. But it seems to me we should be looking for bacteria, as you lay out in your paper. How do we start this process? What do the scientists need to do to start looking?
Well, as I say, we go to Mars. First of all, we look to see if there's life on Mars. Once again, if there's no life on Mars, it means life on Earth originated on Earth, because Mars would have been seeded from the outside. If we find life on Mars that's fundamentally different than Earth life, it means each of them developed their own life form locally. If we find identical life on Mars, but with a pre-bacteria on Mars, that would mean life on Earth came from Mars and it originated on Mars. But if we just find both of them just have the same kind of bacteria, that Earth has the same biochemistry, and no evidence on either planet of a prior evolution leading to bacteria, that means they were seeded from the outside. Now, furthermore, if we want to see if there's artificial stuff going on, one thing you could do is you could look at these Martian bacteria and you say, are any of these carrying genes for higher life forms? In other words, how do you know a spy? They're carrying messages like the plans to your fort, okay? Are any of these bacteria carrying plans for building a fort, as it were? That would certainly show that they are artificial and that they are meant to influence evolution. Or we could look for the micro spacecraft, the systems that would be engineered to allow them to survive interstellar travel, tiny little micro sailcraft, which could be floating around in the atmosphere of Mars, and because they're light enough that they could do that. And we know they didn't come from the Martian surface, because the Martian surface is lifeless. That'd be another way to do it. So we could look for the messages, or we could look for the messengers.
Amazing ideas. Thank you for joining us today, Dr. Zubrin, and everybody check out Dr. Zubrin's new book, The Case for Space, How the Revolution in Spaceflight Opens Up a Future of Limitless Possibilities, where he goes into those ideas about microbial SETI, but much, much more. We live in amazing times, folks. Let's all go to space. Thanks, Dr. Zubrin.
You're most welcome.
That was part 1 of a 2-part discussion with Dr. Robert Zubrin. Be sure to like and subscribe and turn on notifications as part 2 will be released very soon.